start, first of all, by introduction to myself. My name is Nati Shalom. Anyone here know what's the meaning of Shalom? Yes? Peace. What else? Anyone? I know that there are some Hebrew speakers, or at least know the name. So it also means bye and goodbye and go away. Depending, so you could pick up the one that you like. Hopefully I'm going to do some more of the peace part of the world, specifically talking about different elements that usually are debatable in this world, like NoSQL, MongoDB versus Cassandra versus HBase and all those type of things that we used to debate. So I'll try to put things more in perspective and kind of put some more, I would say, engineering thoughts into how you pick the right technology and what are the choices. Hopefully it's going to be more interactive. So this is really more of a framework for discussion rather than a presentation. And the way it's going to be laid out is that I'm going to, first of all, introduce a topic that is called real-time analytics, which is not necessarily new, but not very known, at least not in an engineering perspective, to everyone. Then I'm going to pick up on a case study from Facebook that built and announced a very impressive architecture for doing their real-time analytics. We'll go through the motivation, what brought them to do what they've done, and how the architecture is actually built. And then hopefully we'll have kind of an interesting discussion in which we're going to analyze that and see how we can make things better. At that part, I'm actually going to bring my own experience, and I'll try to draw a solution when I face that same problem, how I draw the solution. But again, the idea is not to take that and say, this is the right solution, but mostly to encourage other type of thinking when we're dealing with these type of challenges or with these type of problems. And hopefully, again, we'll have that interaction so you could interrupt with that, question things that I'm suggesting or not suggesting, and come up with different suggestions. Hopefully it's going to be more entertaining. We'll end up towards the end. If we'll have time, we'll even see a demo that shows some of those principles that I'm going to talk about. So first of all, what is real-time analytics and why is it important? Why is it important today? Why it becoming such a topic even? So generally speaking, if you think about real-time analytics, the past, mostly in financial industry, we're using it mostly for risk analysis. And the idea of real-time means time means something. Meaning that if I'm doing a risk analysis of a portfolio, and I know that my portfolio is not doing well, meaning that I'm losing money, and I know it only a day after, that time between the time actually starting to lose money to the time I'm actually knowing about it cost me money. So the faster I can actually get to the point where I know that I'm losing money and I can act upon that, obviously, is the time that I can actually save money. That in itself was a small niche in the market. I mean, not everyone was running that type of risk analysis. And the question now is why it's becoming a hot topic today? What have changed in the market? And there are several things that have changed. First of all, if we look at a lot of the social media, what happened is that our profile, the profile of each user here, actually each user here have roughly an average 80 pages in Facebook, if you know it or not. So there is much more information about the profile of a user that is now public knowledge. That wasn't really before. A lot of the services that we're offering are SaaS services that are actually served over the web. And our services are starting to compete on how well they know their users. And if you look even on search engine, Google versus Bing versus others, the more they profile the users, the better the search algorithms becomes, and the better the search result that you're getting is better. So there is this hidden war, if you like, between sites on how well they know the users and how well they can actually respond to them. It's not just how well they respond to that and give you better quality, it's also a conversion war, if you like. A conversion meaning that out of the traffic that is coming to my site, how many of them will actually act upon my site and do something that is meaningful for me? And that's kind of, I would say, the general theme for a lot of those analytics. And today, if you build a SaaS company or if you build a SaaS product, if you don't record every action on your site and you don't monitor it and analyze it, then you almost don't have a right to exist. And that's kind of the things that have changed the analytics from real-time analytics, specifically from the point in which it was a niche play in the market to something that is almost fundamental. You can't really build anything without it. And that kind of explains the background why this topic is interesting today more than it was in the past. Right now, what I'll try to do is kind of sketch what I think is the common pattern in real-time analytics, how things, in general in analytics. And I took the slides from Twitter, for example, and I tried to break down some of the statistics that they gather when they build their analytics. And there is a dimension here, an interesting dimension that you'll see here, actually 2 dimensions that are interesting. So the first one is things that are called counting. I'm basically collecting counters about the users that are doing tweets and so forth. I can count, for example, the number of requests a day, and I can count the number of average latency and all those type of things. Obviously, this is information that is continuously updated, not something that I can gather and then look at that. I need to see that all the time, continuously updated through graphs and all those type of things. Then there is correlation, which gives me a little bit more of a correlation between those numbers. So for example, I can ask questions like, how many users are coming from desktop versus mobile, and so forth. And there is a research, which is more of a long-term kind of view. I'm looking at things from the last year, how many people from different continents actually accessed my site, do I have duplicates or any anomaly in the data that I collected, and things on that line. So this gives you an interesting dimension. So if we look at the dimension, we could see one dimension is time. Obviously, the first elements, the counters, are things that I'm counting right now and means something right now. But if I look at that a year ago, a year after, it doesn't really mean anything. It's not important anymore. The things that becomes important is really those things after a period of time, which is the correlation, the trend analysis, and all those type of things. So there is an interesting thing about the time dimension here, okay? When we look at things here, we look at them in real time. We look at here, we look actually at the aggregated version of that same information, not at the same level of resolution that we're talking about here. If we look at that from a technology perspective, we'll see that the way we manage and handle each of those pieces of elements is very different. In the traditional world, we used to have data warehouse and OLTP. OLTP was known to be the transactional system, meaning the web front end of the application. This is where, as a user, when I click something, it goes to a system, it goes to my web server, it goes to a database, and this is where my transaction is happening. The analytics was gathered from that traffic or from those transactions into a data warehouse. And on that data warehouse, we used to build things in a certain way so that it will fit to a certain type of analytics that we were running and knew beforehand how they're actually going to look like. And that was the pipeline of information that most of the website, at least of today, was running on. So for the real-time part, we used to use something that is mostly event-driven. We'll look at those technologies in a second. We were looking at things at a very high resolution, meaning every click of a user matters. Versus if we look at correlation, we were doing mostly ad hoc queries against databases, so we were storing data in databases. We're not doing it in an event manner. We are storing it first in a database, and then we're running store procedures and other things that will look at all the data that we gathered and basically generate those spreadsheets that we were looking at to build our reports. And obviously, this was the batch part of the processing. We were actually crawling across all that information, actually passing it from the database into somewhere else, into a specialized set of databases, and starting to crawl that and crawl that and crawl that until we get the information, because we had to process massive amount of data. Now, the things that happened in the past few years is that the volume of data that we wanted to record, again, remember the case study where you have a SaaS website and you want to record every operation of every user, became vastly bigger than it was in the past. And therefore, a lot of the technology that we used to started to suffer from a scalability issue. And that's why we're starting to see in this area, for example, things like Hadoop coming along. And Hadoop was basically trying to solve the problem on how do we run those batch analytics on massive amount of data. And obviously, that problem started to pop up here and here as well. And this is where we started to see things like NoSQL. And here we're starting to see things where actually happened even before that, which is the in-memory things and things that I'm going to mention in a second. But that's kind of the general idea. The patterns themselves remain the same. It's mostly how we implement those patterns that became different. And let's see what are the alternatives that we were looking at. Obviously, there is the centralized database that was the universe at the time. And obviously, the one-size-fits-all model didn't really fit itself. And we were facing several challenges that I don't think worth even the time to go through that. I think it's pretty obvious. The other part is called complex event processing. How many people here heard about complex event processing? Quite a few. Okay. So complex event processing, think about it as a reverse query, right? Usually we go into a database and we run a query against the database and get a result. With continuous query, think about the top of a market. For example, this is a classic query that fits well with the complex event processing. We want to know the stock, for example, that is at the top of the market right now. If we're going to continuously run that query against the database, against all the stocks, we're not going to be very efficient, right? Every time we're going to analyze the entire market, but we already know who is second, who is first right now. So all we need to know is the delta, right? What have changed from the point in which I know who is leading right now? So I only need to know if someone have passed him or not, and how far he's passed him. And that's a classic case where continuous queries try to build that view based on the changes, rather than based on looking at the universe all over again and build the world just by looking at the universe again. And continuous queries basically holds a period of time, and then every event, it does a correlation between the event that happened and the data that it has, and update the table, if you'd like, the score that it has, based on those events. That's in a nutshell what continuous queries is all about. And that's why I said it's a reverse query, because it's not us that is asking for those queries. It's mostly driven by events. It's something that is already sitting there, and someone is collecting the data and building the result set, if you would like, continuously, and generating that updated report, if you would like. What was the challenges with that? Because of that model, the model itself was trying to do a lot of correlation through a stream of events. The advantage of that is that it was more efficient because we didn't have to go and query a large set of data. But the disadvantage is that it was very centralized by the architecture itself, because we had to do a lot of joins when the event was coming, and therefore we had to put all of those information, all of those events, through a centralized server, which was the complex event server. And that becomes in itself a bottleneck. Okay? So we'll see later on how we can deal with that. The other piece is in-memory data grid, and in-memory in itself, if we look at the trends, we have memory capacity today, even in terabytes of data, that we can buy even in a single server. So obviously there is an advantage that we all know about putting data in memory, and the fact that it's actually can be much faster than having the data in disk. The challenge in that is usually the capacity. Okay? If we're running into the capacity that I just mentioned earlier, where we record every operation that the user interact, we can only store a few hours, a few days of data, worth of data in memory to actually make it worthwhile. Otherwise, we're starting to get to a point in which if we're starting to store petabytes of data, it's going to be very expensive and very hard to manage from a size perspective. So it provides value, but it doesn't really solve all of our problems. And this is where NoSQL came into the world, and NoSQL was really dealing with the two challenges. One of them is the capacity, and the other one is scalability. And it was basically provides a much more cost-effective solution to deal with the capacity aspect and also the scaling aspect. That's, again, in a nutshell. The challenge there is the complexity of working with NoSQL, and also, in many cases, for scaling, the read performance that we're able to get through that model was fairly limited, or compared to other alternatives that I'll mention later on. But it was all centralized around the problem: how do I deal with a massive amount of data at a lower cost, at a more efficient cost, if you like. Hadoop and MapReduce, and people, when usually you mention the name analytics, the name Hadoop pops up almost immediately. It's almost a synonym to analytics. So generally speaking, Hadoop was based or was built for batch processing. That's why I mentioned that batch processing is not really real-time in many ways. Now, the interesting thing is that that realization is now common to everyone, actually, in the market. And I picked a few of the quotes of the creators of the concept of Hadoop. Actually, Google, who was the father, if you would like, of the concept of Hadoop, have moved to something that is called percolator for their search engine, meaning that every time that you're doing something, you write a blog, you're not waiting for a crawler to actually store it somewhere and then it goes to the index of that search engine. It actually goes directly to the index. That's the difference right now. And what happens, as you could see here, is that the more we wanted to be more real-time, the harder it was to do things in a batch kind of processing model. Because what happened in batches is that the more you have more information, you're starting to build something that is called a backlog. You're starting to have more and more data that you need to process. Now, in some cases, the batch is few hours, and you count on the fact that within the hours of the night, you can actually do those processing. And you have that window of time in which you could actually run those batches. There are a few problems with that. One is that that assumption that you have those few hours changes when you start to work globally, because then you always have data that you need to process. There is no such things even as a few hours of the night. And the other thing that is a challenge is obviously the real-time aspect. There is a large set of information that you don't want to wait for the day afterwards that you could actually process and know what happened. For example, if a customer goes to your website, you want to be able to provide him a recommendation on what's good for him right now. Because once he left your page, whatever recommendation that you can give him is not really relevant. If someone is calling the call center, and that's actually a case study that brought me to all this discussion, if someone is calling a call center and you know that that customer is actually frustrated, he's calling the cable company and he didn't get a good service, and the teller is don't really know who is that caller and can't really offer him the right program, then most likely you're going to lose him. So you have to be able to act in real time to actually convert on him, or in the case of the cable company, to actually keep him in the system. And therefore, batch processing answers certain things, but doesn't answer a growing aspect of reports that we want to generate, the real-time part of the reports. So the lessons from here is that we have different bunch of technologies. Each one of them is good for something, but there is no one thing that covers everything. So if you really want to manage all those different views of analytics, the correlation, the counting, and the research, we need to have a bunch of those. And then the main question is, how do we order them? How do we build that pipeline? It's like a manufacturing pipeline in many ways. Because if we are good at batch and we're not good at real-time, then we're going to have a backlog there. If we're good at real-time and we're not good at how fast we can process this amount of information, then we create a backlog there. So a lot of people have started to build those solutions as silos and started to realize that the main challenge is not just how do we do batch alone and how do we do real-time alone, it's also how we make the information flow in a way that wouldn't create bottleneck in the process itself. And that's a big challenge, and we're going to talk a lot about that. So this brings me to Facebook, and what brought Facebook to actually look at that problem, what were the challenges. And again, I thought it's a very interesting case study because it brings a lot of those questions and also an answer, or at least one type of an answer to those questions. So for example, the motivation of Facebook when they dealt with that system is that they wanted to be able to count all the likes and the comments that the user does on the pages. Why is that important for them? Because obviously that increases the impression. Impression is how they make money out of advertisement, right? So the more effective you are in your page, especially for news companies and things like that, the more money Facebook can make on advertisement. And therefore they needed to give you tools to actually make your work better in the same way that Google actually provides Google Analytics for free, okay? So there is this win-win situation in which they have a strong incentive to support you and provide you with that visibility and information. The previous system was providing that information in an accuracy of 48 hours. Now you could imagine what happened when you post something on a wall of a news company, and it happens to be that there is not enough comments on that post because it actually doesn't have the right title, doesn't have the right keywords, or it's actually pushed somewhere down the page. Now, you know that it's not effective only after 48 hours. And let's say that you learn that it's not effective and you want to correct it. And let's say that you even correct it. After 48 hours, especially in news, you can't really do anything. It doesn't make anything. And therefore, you have to be able to give that feedback, again, close to real time. And therefore, the challenge was to move from 48 hours to close to 30 seconds. Now, this is interesting, okay? In one hand, we want to be able to push an analytics that was done for 48 hours into 30 seconds. That's a big challenge. Because now we need to process the same amount of data much faster, right? On the other hand, we want to be able to do things that will enable us to do that without any failure. So it needs to be reliable as well, much more reliable than it was in the past. So, and the reason why reliability is important here, because you would think that batch and reliability, you have much more room here to play with, right? But what happens when something is not reliable, even in analytics? Especially think about a counter. You're doing a plus plus on something, and you're missing some of those plus plus. What you're starting to get is, for example, we actually have that problem in our Google Analytics, that in some cases the analytics is 100+% of conversion, which obviously is not something that is acceptable. And immediately when you see that, then you look at the report and you're saying, it's unreliable, but I can't really look at any of the data because I can't really trust that data, and the report itself becomes useless. And therefore, reliability equals accuracy. If it's not accurate, the report is useless. And if you can't really build a report that is accurate, then you can't really, it doesn't really mean anything for anyone. And therefore, reliability is important from an accuracy perspective, not the same thing that we have in transactional system where it is important because if we lose data, then we actually lose transaction of people and things on that line. It's more important from a reliability, from an accuracy perspective. We also need to deal with not just that we want to squeeze the time it takes for us to do the analytics, we want to be able to handle much more data. I mean, in terms of the amount of data that we want to deal with, or at least Facebook, 20 billion events per day, which is a big number, right? By all means. So how did they come around that? So first of all, before that, I just wanted to give you an idea of how those reports looks like. So for example, what you could see here is something that is called a funnel. You could see here the number of people that was coming to the page and actually the people that was clicking on the like button. So this is an information that we can use and know how effective we are in our page, in our posting, and those type of things. Obviously, it wasn't meant for individuals. It was mostly meant for news companies in that regard. The same thing for comments. Again, we're collecting the data of how many people visited our page and how many did something, acted upon a news, acted upon something that we posted on that. This is the interesting information that they needed to collect. So what is the information that they need to collect? Per URL, they need to be able to know the counters, meaning the number of people that actually clicked on like, clicked on comment, click on that, and that enables them to build those graphs. That's generally the idea here. Okay, that's what we're trying to achieve here. What did they evaluate it? They obviously looked at almost the entire universe of things that you could use. They looked at MySQL, and the reason why they didn't pick it on MySQL, even though Facebook runs a lot of data on MySQL, is because to do those counting, this plus plus thing, MySQL wasn't really effective of that. It was trying to solve a much bigger problem, which is complex queries, and now we're dealing with counters, which is not that complex queries, and what we have in return is that it's actually not a good fit for that type of problem. In-memory counters, Facebook is based on Memcache, and there is a large piece of data that is actually running on Memcache. Memcache itself would say the default implementation of Memcache is not reliable. And therefore, if we remember what we've talked earlier, we have to make the counting reliable because otherwise the report itself is useless. And that's why they actually disregard that option. MapReduce is not real-time. We've already gone through that. And this is the other interesting part. They actually tried Cassandra and HBase. Obviously, Facebook is known to be one of the contributors to Cassandra. So that was interesting to see what they would pick. But they're also very heavy users of HBase, and I would say even heavier than in Cassandra. So again, the problem that we're trying to solve is collecting counters and doing these plus things continuously on those counters in a reliable fashion on large volumes. Okay? So at the time when they evaluated HBase and Cassandra, HBase had an advantage on how they manage counters compared to Cassandra. Let's see what happens afterwards. But that we'll see. I'll keep you a little bit in tension. We'll see that in a different slide. So if we sketch the solution, and I was basically doing a reverse engineering on how they describe their solution and build that diagram, which apparently is a close estimation to what they've done. We're seeing the following architecture. This is your web. This is you. And you're doing some clicks here on comments and posts and all those type of things. And there is an AJAX event that is generated per action. And that AJAX event is being stored through something that is called Scribe. Scribe is an open source project that is a log, basically a log framework. Okay? And they're storing all those logs in something that is called HDFS. HDFS is the file system, again, part of the Hadoop framework. Any reasons why they would put it in HDFS and not in regular file system or storage? Excuse me? It's more scalable, but the file could be fairly big. What else? And I can tell you that that's actually not the primary reason. Clustering, reliability. Remember the reliability? Okay? They needed to be able to store things. Again, when you record something, and think about how you record even a movie, right? You don't want to lose a frame because it might be the important frame that you're losing. You don't know what you're going to lose. And you don't know how it's going to be important. So the most important thing is to record everything, all those frames, in the most reliable fashion so that when you do the editing afterwards, you'll be able to pick up the right ones. And maybe throw 90% of that. But still, you wouldn't lose anything. Because it could be that the one that you lost is the one that is important. Okay, so we said that we had to store and record everything reliably so that later on we could actually analyze it and throw the rest or throw the part that are less interesting, but we don't want to lose any frame of the things that we're recording. And HDFS gives us that reliability aspect. Okay, and obviously scalability. PTEL is a service, and Puma are not part of the open source framework. They used to do the aggregation. So basically what we do in PTEL and Puma, we collect the logs and then generate an aggregated view of them, aggregated counters, that is stored in batches into HBase. Now you could see that the batch size itself is 1.5 seconds. We'll get back to that later on. But this is an important number here. Part of the reason for that number relies on the capacity of memory that they can actually, meaning the amount of data that they can actually store for that batch in that single process. Now, another interesting thing, if you look at that picture, is that that thing is distributed and that thing is centralized. Now, if you think about scalability, and anyone that draws a scalability pattern, the first thing that you're trying to do in scalability, like scalability in traffic, the way you scale traffic is that you put more lanes, right? But if you have a certain place where you have a junction, you have a traffic jam, just because of that. It doesn't really matter how many lanes you have heading to that central junction. So this potentially could be a scalability bottleneck. Now, one of the ways to solve that is through that batch, because we can push the barrier and actually let that single point deal with more traffic than it used to. But it's still a potential bottleneck in the architecture itself, and I'll touch on that later on. when we analyze, remember the first number was 2 billion events a day? When we actually looked at that and analyzed it, and actually looked at the number, like how many events they actually deal with per server, the number was 10,000 writes a second per server, which is still a big number, but not non-realistic. Why is that important? Why do I mention that? Because usually when we read the reports and we look at those numbers, we're saying, well, we'll never be able to do something like that ourselves. But actually you could. Because really, if you look at that, and part of the things that I wanted to show you through this presentation is that you could actually build something better, much better than that. So it's not that far high. In many cases, the story and the numbers doesn't really tell the full details. And when you know the details, you can actually think even on how you could do that much better. So a few things about the assumption that we started with, right? Remember, we started with the assumption that memory is not reliable. Now, if you look at how they designed the system to actually meet those 10,000 requests a second, if they would work through Scribe, the log file, and try to write everything directly to disk, they wouldn't be able to deal even with 10,000 requests a second. So what I tried to do is basically squeeze the amount of the size per log and the actual buffer so that it would fit in memory itself. So at the end of the day, they do rely on memory to actually meet their goals, the performance goals. The other thing about Cassandra, and this is where I'm coming back to you, is that at the time when they evaluated Cassandra, there was a difference between HBase and Cassandra and how they deal with counters. But the latest release of Cassandra actually fixed it. So the question is, if they would evaluated HBase versus Cassandra today, would they come to that same result? And what is the lesson here? The lesson is that in many cases we look at those benchmark or decision making and we're saying, well, if Facebook picked up HBase versus Cassandra, then it must be that HBase is better, and we don't even bother to evaluate that ourselves. But we forget that at the time in which they evaluated it, things may have changed. And in the NoSQL world, things are changing quite fast and quite rapidly because it's a fairly new market. And therefore, we can't really take that as an assumption. And I know for a fact that if I would do that same evaluation for those same requirements, I would probably pick up Cassandra and not HBase, for other reasons as well, not necessarily just the performance. That was an important thing that leads me to that point. Now, we've seen what the challenge was. We've seen what Facebook did to actually build a solution for that challenge, which is actually a good solution. All the principles are actually in the right place. And the question is, can we do things differently? And before that the question would be, out of the assumption that led Facebook to go with that solution, could we have a different set of assumptions that will lead to a completely different solution, potentially? And I tried to kind of question the assumption before I actually draw a solution. And obviously, if the assumption can be different, then you could assume that the solution could be vastly different. So for example, one of the assumptions is that memory is not reliable. What if it could be reliable? And I can tell you that it could be reliable. This is what we've been doing for a long time. The decision about NoSQL, we can see that the decision itself, especially in this time, is very hard, because the market itself is moving very, very fast. There are a lot of different solutions out there, and each one has an advantage, the other one has disadvantage, and we have to be very, very specific at the time in which we're making a decision on what we actually want, or what we actually need to pick up the right solution, but it's a very dynamic world right now. So how do we deal with that? Can we even say we can pick up this versus this and live with that for the next 10 years, or 3 years, or even 2 years? Can we? I'm not sure. And the other challenge, which is an additional requirement that Facebook don't have, if we need to build a solution out of, let's say it's a product that we want to deliver, then having a setup that runs in a certain data center that is well-defined, that is well-known, is different than shipping a product. Shipping a product meaning that you need to be able to package it in a way that you could clone it very easily in different environment and it will work. The more moving parts that you have in the solution itself, the more complex that solution can become. So this is another requirement that I added to that same challenge that I mentioned earlier. Because what we want is to create a solution that you could package for that same problems almost everywhere. So how do we improve that? And what are the principles and what are the steps that we could actually improve? So the first one that I picked up is this one. And for that point, I want to have more interactive solutions on what are the other improvements that you think might be good. And then I'll jump into some of the solutions that I made. So the first one that I said, if we can assume that memory could be reliable, we can actually put the log, instead of in HDFS and log file, we can actually put it in memory. Right? It will be faster. It will be potentially more efficient. Anyone sees a problem with that? Yes? What is it? It's not durable? Oh, you asked the question and you also answered it. Yes, so the question, the point was that it's not durable, meaning reliable, meaning that if one of the processes goes down, we actually lost that window of log, and we remember what we said, we don't want to lose any of that part. And the answer was also, it's probably replicated. And the answer is that to actually make memory reliable, you do the same thing that you do with disk. Because this itself is not reliable if it's not replicated. That's why you have RAID, for example. So the same thing applies to memory. Yes, you wanted to say something? Right, so there is the question of capacity. I'm going to actually put some numbers here towards, I think, 2 or 3 slides from here. We're going to talk about capacity, but capacity could be a challenge here, right? Remember, 10,000 operations per second could lead to a huge number. So the question is, how do you deal with capacity? And capacity could be a challenge. So in some cases, memory could be a good solution. In some cases, and it will be dependent on the capacity of the amount of data that we're dealing with, it might not be the right choice. But we'll actually take the numbers from Facebook and compile them and see what is the capacity that we need. And see if the answer to that is realistic or not, from a cost and from a size perspective. Okay, but capacity is definitely an issue here, or potential issue here. Other things? Yes. Yes, so the question is, did we compare between Memcache and data grid solution? The answer is yes, and there is a difference, and I'll touch on a few of those differences. One of the differences is the assumption about reliability, okay? With Memcache, at least the default implementation, now there is a commercial implementation of that actually deal with that, but the default implementation of Memcache is not reliable, meaning that if one process fails, you assume that you could lose data. Where in this case, we're assuming that we don't lose data, and data grid was built with that assumption in mind. They were built as a system of record. They were built mostly as a database in memory, distributed database, but with the same assumption of a database. And therefore, data grid are different in the sake that they're reliable. There is another aspect that is interestingly, with the data grid is the API itself is far richer in terms of the queries and the language that we can actually interact with. For example, we support JPA and we support Document API and SQL. Others support a subset of that, but also a much richer API than you would get with Memcache, which means that unlike the log file that we used in the case of Scribe, we can actually store the data in this in-memory log, but also query that as it flies into the system itself. So remember in the previous solution, when we actually store that information in the log, we can only see that information only when it actually was written to HBase. Up to that point, we couldn't really access that information. And I'll tell you when it's going to be important and what type of application would actually want to see that as it flies. As it gets into the system, why even want to bother and look at that immediately? And I'll give you some case study for that. But that's another good point, the difference between Memcache and data grids. If we look at the assumption that memory is not reliable and we apply it to Memcache, then the answer, yes, it's not reliable, therefore we'll go with the log file. But if the assumption is that we want to leverage memory, and by the way, again, in the case of Facebook, they leverage memory in any case, because they would never be able to get to 10,000 requests a second without forcing their model to fit into memory size. That's what they did. Remember the Puma and P-tail and all those other things? What we're basically doing, again, think about a pipeline. We have information coming in to our pipeline, and then someone is picking it up and then storing it. Now think about a manufacturing pipeline of a car, of the bottles of Coca-Cola, or anything like that. Any pipeline would do. Now, if you have people that are sitting in different factories, what would be the process of passing that goods between one factory to another, right? You would be doing something in this factory. Someone would need to ship it to another factory. And then that needs to go to another factory, which obviously takes time. Versus if you put them in the same building. If you put them in the same building, obviously the time it takes them to pass the goods that you managed and the goods that the other guys in the pipeline takes would be much faster, right? So if we see an area in our architecture that requires that level of dependency, then it's much better to put them together. But if they are less dependent, they can live in China and do something for me, and I can get it a month later, and that's fine. I can actually distribute it. So the thing is that if we see that in our pipelines there is strong dependency in any case with the components of our pipelines, then we better collocate them. In this case, the log and the Puma have a very strong dependency. We have to push all that thing very fast, and if one of them is not working at the same pace as the others, the entire pipeline starts to break, because then we're starting to get into backlogs, and therefore the decoupling can be a diminishing return in many ways. We're not really gaining that much out of that. We potentially gain, but we're not really gaining, because we're as strong as our weakest link. And therefore, the optimization was to keep the same separation logically, but collocate them differently, meaning I'm taking the things that I feel that are strongly dependent from a runtime perspective, decoupled from a functional perspective, and put them together and then assembly them together, and this becomes something that we use to refer to as a processing grid. Okay, so in this case, we did two things. One of them, remember that the Puma itself was a centralized point. We basically created that as a virtual point. It's not a central server anymore. And the second thing is that we actually collocated that with each of those data points, and therefore we can actually process the data collocated to the event itself, and therefore we can process larger volume of data. So we solve two problems here: the centralized Puma and the speed of processing. Other optimization that you can think of? Is there any optimization? How would we store to HBase in this case? Would you? You mentioned the challenge of capacity, right? So if everything here is in memory, we're going to run out of data. So where would you put HBase or Cassandra in this case? What's that? Per level, yes. So basically what you're suggesting is that you could actually put, and you're actually stepping a step even further, you could actually put a Cassandra or an HBase instance per node here, and that means that virtually they look at one big database, but each one of them can persist, and therefore we'll have a segmentation of the short-term data and the long-term data. The long-term data would live in HBase, in Cassandra, or what have you, and the short-term data would live here. Obviously, Cassandra in this case, or HBase, would hold all of the data, and that's even another optimization. But that's an answer to the capacity challenge, right? If you remember the time window that we have, usually when we look at the data, we deal with that differently based on the time and the resolution of the time. So in this case, we could have the first day would live in memory, and the last year and 7 years would live in disk, and so forth. So we can separate things in this way, and that's how we can manage the capacity. We can even go further and say that the only amount of data that we need to store in memory is only the buffer before it's actually written to HBase or Cassandra, which could be only 15 minutes or 1 minute, in which case it's not going to be huge, right? Because we only need to store the amount of time before it's being committed to disk, which is not that big. We're going to come back into that later on. So this is a code snippet of how that thing would look like. And the reason why I put that code snippet is to show you how simple it could be and what is the type of things that you need to do to actually write that processing. So we can see it's something that is very close to people who are familiar with JMS and MDB. It's very similar to that. It's just a Spring-like MDB. We can describe here, we can have a listener here, and we use a notation to say that that listener needs to listen to events that comply to a data that is called data object that has a property with a value of false in its property. And then whenever there is an event, that method will call for every data that has a false value in this property. So to build something like these counters on Google, all we need to build or to write is those snippets, which is very small, that basically will do count plus plus. So the answer is really to use something like write behind, and in this case we do a segmentation of the data. We're not storing all the data in memory, obviously. We're storing part of the data in memory. The data could be the data only before it, the stage data before it is being stored, or it could be actually bigger than that because we can afford to. And we're going to be able to remember the other challenge that I mentioned earlier was that the world of NoSQL is very dynamic. So one of the things that we can gain by that is that we can decouple the underlying data source by putting here something like this, a generic data source adapter, that all it needs to do is basically takes those events and do an insert, a simple insert into the actual underlying database. In that case, the database could be different things at different point of time, and we could pick up the right one without necessarily affecting all our analytics processes. Obviously, there's going to be another layer that is going to be dependent on the database itself and is going to be changed, but at least we marginalize the area in which we're going to be dependent on a specific API of a specific database. We're not going to avoid locking completely, we marginalize the dependency. That's basically what we gain here. The other thing that we gain in here, remember eventual consistency, right? Anyone remember that? So eventual consistency was used as a model to enable us to deal with scalability of write, if you would like, of scale of writes, and the way we dealt with that, and obviously without losing at least the availability of the application itself. And the way we dealt with that is that we actually compromised on consistency. Okay? What was the problem for that? Try to write a program that would write something and would assume that the read and the write are not necessarily consistent. It's not that easy to write an application like that. It's not that easy. I mean, there are certain cases that will fit that, but there's a lot of other cases that won't necessarily fit into that. The thing that we're getting here is a different degree of compromise between consistency and availability. And here what we can see is that we created a layer that is consistent at the front end, so the application itself gets consistent interface. Whenever we hit the data in memory, we know that it's consistent, that the write and read are always consistent. But where it can be more flexible on how the data is pushed here. In this case, we could use eventual consistency, because the online part of the application, the one that needs that consistency, because it's very real-time in a sense, it's not really dependent on that. Actually read the data and the counters from here. And therefore, we have an interesting model by doing those decoupling that we can actually build a system slightly differently in terms of the compromises that we have. We don't have to have the entire system eventual consistent or consistent. We can actually have part of the application consistent and part of the data eventual consistent. And this would give us even a better trade-off. Remember the cost. So before I jump to that slide, those who haven't seen it, those who have seen it shouldn't participate in that answer. Yes? Yes, yes, yes. So for example, if I would try to write something here and then read it from here, the write from here and the read from here wouldn't necessarily be consistent, because there's going to be a time until it's actually going to get there. So the question right now, again, back to your question, is what is more expensive, memory or disk? Anyone have a guess? What is it? It depends. Okay. You shouldn't answer that question. Anyone have a guess? Memory or disk? Come on. Memory is more expensive. Yes, right. Well, it depends. It depends, and I'll give you a reason why. And usually I have, I think I found a good analogy to explain the thing that is, at least presumably is a big anomaly. Think about a container. Now I give you a container that can store 10,000 bucks within that container. It has a certain box. Now I'm telling you that you need to be able to pull those goods within that container within an hour. Okay, you're in a port, you need to be able to, you're getting paid for the time it takes you to pull those boxes from that container. Now I give you for the same price a container that is 10 times bigger for that same price. How long will it take you to pull those? Right now it's going to be 10,000 boxes. Let's say that previous to that it took you an hour, 10 hours, right? The reason why is because the door to that container is the same, meaning the access time to pull those boxes haven't changed. That's what happened to disk. The capacity increased, but the access time didn't, or at least not at the same pace as the capacity, which basically means that we can't really, if we want to access all the data, if we want to store it and not access it, then that's fine. But if we want to store it and access it and read it, then it's actually going to be slower. Therefore, there is, when we measure the cost, we can't really measure the cost per gigabyte only on the capacity. We need to measure the cost per throughput goal. So for example, if we need to, if our requirement is to keep and be able to pull those 10,000 bucks in an hour, we'll need 10 containers. Versus if we'll put a container with a much bigger door, 10 times the door, we could still do 1,000 boxes an hour in one container, because it has a much bigger door, and that's memory. Okay, so that explains the difference between memory and disk, and when memory can actually be cheaper than disk. Because if we need to deal with 1,000 requests, or in this case 10,000 requests a second, if I only go with disk, I need a lot of servers. And for memory, I need only one server, or even less disk. And that's the interesting aspect here. That brings me to this one, which actually also addresses the capacity aspect and the cost of capacity, because I think a lot of people coming with that assumption, and I did some exercise here. So for example, this is a Stanford report, so whatever I said is actually backed by a research that was done here. It's not just my thought. And obviously for long-term data, disk is actually lower. So the most optimum solution from a cost perspective would be to combine the two. This is where the name Shalom comes in. Remember? I said that I want to make peace between things. So in previous presentation, I said only that. Now I'm saying the two things. Okay, so coming back to the cost. So if I'm taking, let's say that for every URL, a message of 500 bytes at a rate of 10K messages a second, the only thing that I'll need is roughly 16 gig of window if the window itself is an hour. And by the way, I don't necessarily need an hour. An hour is the time between the data that is written. In some cases, I only need 10 minutes. But I took an hour just for the sake of exercise. So if I need an hour to store 16 gig, that will cost me $32 a month, which is like a Starbucks every day. That's the cost of having the same throughput of Facebook in memory. The other assumption in many other sites is that most of us are not Facebook and have even less throughput, which means that it's not going to be $32, it's going to be even much lower. So that's kind of ideas that hopefully will break you from certain dogmas on how you should do things or could do things. The other thing is the operational aspect. Remember the third requirements that I added to that, that was coming from that other project that I dealt with, is that it needs to be simple. I can't really have 5 or 10 people, and that was the case in Facebook. They had 10 people working on that project. Oh, sorry, 5 people, not 10, 5 people working on that project from a developer's perspective. Not every organization can afford that. And that's the hidden cost that people are not counting. And if I want to reduce that cost, I need to be able to have a very simple solution how I want to operate and manage that type of application, which means that everything needs to be automated, scripted, and consistent. The way I'm going to manage things needs to be very consistent. How do I do that? I think Adrian is here from JCloud. So he's part of the solution. So generally speaking, we want to be able to leverage the economic of cloud or economical scale to solve a lot of that problem. And I try to kind of put some metrics that maps to that cost. So for example, automation reduces the operational cost, the manual work, and there is a lot of cost associated with this. Elastic scaling enables us to reduce the cost because we're moving from static provisioning to more elastic provision, on-demand provisioning, and we can leverage cloud and other things for that. And more interesting, something that most people don't really realize is the cloud portability aspect. If we are not bounded to Amazon, for example, we can pick up the cloud based on its location, because there is a latency cost. If our data center sits somewhere and there is a data center much closer than the data center of Amazon, then we can pick up a data center that is going to perform much better for us. It's going to be much closer to us, so it's better to pick it up. Or we can be more flexible in how we can actually bid for a price, because if we know that we can work with any cloud provider, we can go to those cloud providers and say, these guys give me this price, how much can you give me for that? And for the type of workload that we're talking here, there would be a lot of cloud providers that will give you a better price than you would get from the list price perspective. So cloud portability means money. It's not just a nice feature, it's actually can give you a lot of flexibility from a risk perspective and a business perspective. So is the case for cloud bursting, which is a different topic that I'm not going to talk too much about it, but the ability to obviously scavenge resources when I don't have enough resources in my data center can potentially give me a way to manage the cost of running my application, because I can never predict how much load I'm going to hit. If I have a flexible solution that could get those resources only when I need to very quickly, then I can avoid those over-provisioning aspect that people do today because of that certain moment in time in year that they expect. So this is the last optimization that we'll have into the system itself. This is kind of putting it all together and kind of showing how all this architecture looks like. And generally speaking, what we have here is the event coming in, then we have a data grid that is basically not just the data, but it's also a processing unit, because we collocated the processing. And what we do within this data grid is a complete processing of the events as they come in. So we can actually also enrich the data before it is being stored, and do all those other things that will massage the data so that when we'll need to analyze it and read it, we can get the data actually ready for those reports and queries that are more long-term. So we can, and then we have something that is called write behind, that takes everything that is written here every few seconds or every few minutes and write it and record it into the underlying database. Because it is decoupled, it could be a generic plugin that can plug into anything here. If I would need to pick something right now, I would probably pick Cassandra, because Cassandra has, especially if we look at the requirements of the ability to duplicate things, Cassandra is much simpler from an operational perspective to deploy. And for us, that was important. If I need to clone a solution, I need to distribute it, redistribute it. Trying to do that with HBase is a nightmare, at least right now. And Cassandra comes with a much simpler architecture on that, and in my view, a much better one. The analytic application itself could actually access the information here or here if she wished to. I mean, in some cases, you could only access the information here, and that's fine. You could use JustPay, or you could use your own abstraction on top of that and access it like that. Or you could have two views, where you could say the last day, the first day is always here, and the rest of the day is here. And it could be two different tables that you would look in your reports. One that you will pick here, for example, the stream of events or the stream of things that the user is doing on your website, you could actually pick here and see that online immediately as they are written. And all the counters will come from here. Okay, so you could actually build a solution that has an interface to each one of them. And we can even use something, and that's, most people don't even know, that we can actually access the in-memory through a standard JPA and do things like MapReduce in a very simple way. So this is a a MapReduce that we added to a JPA interface using the standard JPA API. So in this case, what I'm doing is I'm writing a script in Groovy that will be executed and passed from the client into the server. So each server here is going to run that script. And at the end of the day, what I'm doing is basically getting the results. Obviously, this script doesn't really do anything. But imagine that I need to do a max or min or any type of counters. What will happen is that when I'm doing this operation, this will run in each of those nodes and will be aggregated for me at the client side. And then I'm getting the results here. So I can actually do that and access the in-memory as if it was an in-memory database, and I can actually build a lot of the dimension of data directly from there. And that's kind of where the two combination could fit in. From a performance perspective, I picked up one of the customers that actually built a solution like that, and that's not my slide. And what you could see, remember the 10,000 requests a second? So this was the number that they picked up when they compared it to actually that was compared to remoting with EJB. And you could see that the numbers was 5 times better. So remember the containers that I mentioned? So just by doing that, that means that I need less servers to meet the, or at least a fifth of the servers to manage the same throughput as Facebook in this type of workload. So that was another interesting aspect. Again, you could go to gigaspaces.com and find the presentation, the information, and also on your site. And the demo itself will be available for download as well as part of that, so you could also play with that. So hopefully you enjoyed it. Thank you very much.